No. So, welcome. So this is the title of the course. Although S3 may have acted on some nouns in there. I am and you're certainly welcome to use that part of my name. My office is along 205. My email is and that's my landline number, which I'm sure you all are clamoring to use. That's still required on the syllabus for reasons that are beyond my comprehension. Anyway, so my office hours this semester. Seven to 8 p.m. and then 10 to 2 a.m. to p.m. Monday, Friday. And you're welcome. Sometimes the 10 may, and obviously I'm not in my office till exactly 8 a.m. because I got to be here, and sometimes it might take me like I might be back at 10:05 for my next class. You all are welcome to come by at any point. The syllabus is posted on the Canvas page. And I also on the web page for this course, which is also, you can find it on my web page, or it's linked up the Canvas page. There are, and you should expect homeworks in this class somewhere in between every week and every 2 weeks, probably something like that. We'll just kind of see how it goes. Everything in this class will be on homework. Please turn in the homework. I'm gonna actually have you guys upload it to my Canvas, and then that way it will kind of always be there for all of us. So the notes. So you all, I'm in the process of writing a book. We'll see if that ever happens. But you all get to be my guinea pigs because I've started kind of putting that together. You will find them hilariously full of typos, things like this. Let me know if you see anything. I'm going to try to go through and catch them as we go along. And we're probably not going to do all of my notes because my notes do a little bit more than we've got time for in this course. But everything that I do should be in the notes. And they are on my, at this point, they're on my course webpage. I don't have them linked on Canvas yet. They're linked off mine because I'll probably update them more frequently. So, any questions on the implementation of the course? Okay, so y'all have different backgrounds in here. So I'm gonna start going through the notes talk. So if there's any questions, slow me down. This is obviously a topics course. This is for you guys, not just my crazy ego. So you know, this is your course. So feel free to help me control the speed if you like. And we can kind of do other things or kind of get deeper into stuff as we go along. I'm going to start off with some general ring theory, and then we'll kind of get into it. We're going to need some ring theory to do this. So you will get in this course a little taste number theory. I think that we've got a new faculty member, Robert Dix. I think who will probably, my understanding is he'll be teaching a number theory course in the spring for a deeper and probably better treatment of that. This is part of it. I would recommend that. Factorization techniques, what do I mean by that? Well, so this is just kind of, this isn't sort of informal notes, this is kind of my advertisement for the course that you've already signed up for in a certain sense. Well, what do I mean by factorization? This is the study, so this is what it sort of first meant to me, of the multiplicative structure of a ring. And by ring here, I always mean ring identity unless I explicitly tell you otherwise. Things get bad when you remove commutative. Things actually, in one sense, might even get worse when you remove an identity. So, you know, from the days old, we have the integers and we learned our multiplication tables. You guys probably learned it in fourth grade, kind of thing. And then this allows you to do things in reverse. You factor things, 36. Well, that's 6 times 6. It's also 2 times 18. Or you can get way down to it, and it's 2 squared times 3 squared, right? So factorization is sort of a study of the multiplicative structure of a ring commutative with 1. And let me also say, usually, does everybody raise your hand if you don't know what an integral domain is? Let me kind of remind you, an integral domain is a commutative ring with identity. That it has to have identity. And if you have A times B equals 0, that means that either A or B is 0. There's actually been a lot that was done by Dan Anderson and some of his students on factorization in rings that had 0 divisors in it, and it is a nightmare. I'm going to show you some stuff about why it's a nightmare later in this course. But for right now, I'll assume, again, my sort of default domain. Now, one can make the following observation. The non-zero elements form a monoid. How many of you are familiar with the term monoid? So that's okay. So, well, if you're not familiar with this, what this is it's a group without the assumption of necessarily having identity. If you have A and B and M, then AB is in M. You have associativity, and you have the identity. And here I'm going to assume my monoids are hidden, right? The order doesn't matter, right? So here's the important thing about being a domain. If R is a domain, an integral domain, then for all x, y, for a pair of elements x, y that are non-zero, then xy is in R minus 0. And so you need the ring to have no 0 values for this to be closed under multiplication, right? And of course, since I assumed that it's a domain that's got an identity, so I've got that going on, and I get the associativity just by the assumption of ring, right? So the study of factorization in integral domains, well, that's always been kind of in the background, at least in number theory, right? And I'll explain the significance of things like Fermat's last theorem later. But factorization in general domains got a real kind of renaissance in 1990. There was a very famous paper that was written that talked about various types of factorization properties that various integral domains that have. And then, probably shortly after that time, there was a big school of folks in Europe, in particular in Italy and Austria, that said, hey, ding dongs, why are you just looking at integral domains? Let's get down to brass tacks and just look at factorization and monoids. So factorization. So when you talk about factorization, you can talk about it in an integral domain, but in a certain sense, people are like, well, why do you mess with that? Because when you have a ring, you have this other operation plus that you're not really thinking about at all when it comes to factorization. So why even bother? Let's just develop this whole factorization in monoids, which you can do, and is actually a very, very wonderful tool. But let me give you kind of an example that I'll just kind of hopefully wow you with a little bit, and we'll talk about why it's true later. Let me give you the simplest monoid that I can think of. One of the simplest. One of the simplest groups that I can think of is the ordinary integers. So here's the analog of the simple monoid. Now, notice that, of course, the way I've written this down, this is an additive monoid, right? And I've been talking about multiplicative, but you can translate multiplicative notation to additive here. So let me kind of give you. So let me give you kind of what I mean by that. You can think of this monoid. This is additive, but you can also think of this as this thing can just easily be written multiplicative, right? The 0 is the additive identity here, which corresponds to 1 here. And you can think of these things as sort of powers of x, right? For example, x times x squared is x cubed, which translates to the 1 plus 2 is 3, right? Okay, so if you look at this monoid, so let's look at the additive one here. 0 is the identity. Do you see any elements that are irreducible in the sense that they can't be broken down non-trivial? Is irreducible. I'm going to formally define irreducible, but here in my introduction, I'm going to go with it. What does it mean to be irreducible in a ring? It means that if you can take the element and factor it down into A times B, one of A or B has to be a unit. Here, what do I mean to be irreducible? If one can be written additively as A plus B, then one of A or B must be 0. Right? And 1 is the littlest one, right? So it's easy to see there aren't any negatives in this. So there's no way to break down 1. Is that the only irreducible? Yes, it is, because anything can be broken down into sums of ones. 2 is 1 plus 1, 3 is 2 plus 1, and so on, right? So this is the only irreducible. Now, here's a question. So I'll allow you to answer this in kind of loosely. Can anybody think of an integral domain where the irreducibles behave just like this monoid?
The two adjoin X.
Okay, so first guess. I think you're gonna have to field 2 elements polynomial ring. Is that gonna work? How many irreducibles does this have? This one has what we professionally call a boatload of irreducibles, right? X is 1, X plus 1, and actually, this is a finite field, and so actually there's an irreducible polynomial for every degree, right? So, right? So this isn't going to quite work. You can modify your example a little bit, but how do you modify it? Or do you want to take another example? This one doesn't quite. This has too many irreducibles. But what's one thing you got right, Adam? That's somewhat, this has too many irreducibles, so it doesn't exactly match this, but they do have an important property in common. Do you know what it is?
Well, X follows that pattern.
X follows that pattern, and in fact, any other irreducible will follow that pattern as well. This actually has unique factorization, as does this. The difference is this only has one irreducible, which actually happens to be prime. This has infinitely many. Okay, modify. How can you get one with essentially only one irreducible?
Like one general.
I was gonna say that.
Right, that's kill it all. What's it? All the others.
Localize that.
So you should give more complete thought to this. I don't know if that one's gonna work.
Oh. Well, look like the super ring where you adjoin 1 over n for all irreducible n that is an X. Bad way to describe it, but that's localize it.
Okay, actually that'll work, right? If you localize an X, you only have one irreducible. Here's another one. Because now 1 plus X unit, and right, any polynomial. So actually, it turns out that any non-zero non-unit is actually a power of X times a unit, right? And so basically, X corresponds to the 1, X squared corresponds to 2 times 2. This so if you look at the monoid factorization, basically what you have here, 1x, x squared, x cubed. But there's actually another difference here. Does anybody see what it is? Got a lot more units. Got a lot more units, right? In fact, this thing, the monoid, only has 1 unit. Whereas this thing has uncountable units, right? See if you can pare it down further. That one's a taller order. Let me give you another. Let me adjust this a little bit. Let me make sort of what I call the second most simple monoid. What I want with this one is this is the smallest monoid, or this is the smallest submonoid of the natural numbers union 0 that contains both 2 and 3. Okay, we'll see what we got. If we have to, if it's a monoid, it has to contain 0. And it contains 2 and 3 because I said so, right? So what else?
5, brings 4.
Okay, it's got 2, so it's got 4. It's got 2 and 3, so it's got 5.
Everything but everything.
Everything after this, right? 6, because now I can just add 2 to everything and chain it out. 2 plus 3, 2 plus 4, 2 plus 5, 2 plus 6, and I go forever, right? That's an awful fancy way to say, just remove 1. That's essentially what we've done, right? Okay, for this one. What are the irreducibles of this model? Mhm. Exactly. Because in fact, if you look at what we did, everything else is built up out of those, right? This is 2 plus 2, this is 2 plus 3, and so forth and so on. Okay. And this, I think, might highlight some of these forms of units here. Let me point out kind of another nice property of this. By the way, does this monoid have unique factorization?
No.
No. Can you give me a bad example of factorization? It's always with the 6, isn't it? 6 is an element of this monoid. And I can put this together, factoring, sort of writing additively. You know, I should erase this board thoroughly when I'm done with this class. It's kind of embarrassing, and like 3 irreducibles here, 2 irreducibles here, right? So not only do you not have unique factorization here, you don't even have unique lengths of factorization, right? 6 is like 3 irreducibles one way and 2 irreducibles another. But it does actually have a near unique factorization problem. This is kind of stretching it a bit, but anybody see what it is? I'm gonna make it clean. I claim if M so suppose you have any non-unit element of M and well, let's see. So suppose, and that's not a misprint, I do mean K on both of these. Suppose I can write M as a sum of K irreducibles one way. And then I can write it as K irreducibles perhaps some other way. Then there exists sigma in SK such that pi I equals tornado sigma I. Which really, okay, that's just me fancy saying that these factorizations are the same, right? So this is just a rearrangement of this. That's not really clear. So let's actually prove this. Okay, I can quickly make this whole statement easier by noticing that in M, the only irreducibles are 2 and 3, right? So 2 and 3 only irreducibles in M. So suppose M is equal to let's say this is A of them and B of them here. And suppose C so suppose that I can write in these two ways, right? So this gives me a couple of equations here. 2A plus 3B is equal to 2C plus 3D. Right? Because that's what's on the set. And there's another equation. And what is that?
A plus B equals C plus D.
Correct, because I wanted to assume that the lengths are the same. So I have A plus B, C plus D. So multiply the second one by 2. Well, -2. And add these up, and what I get is B is equal to D. Right? Fantastic. And if B equals D, these cancel out and I get A equals C. And there you go. These two are equal and these two are equal. By the way, notice this monoid does not have any factorization because of this, but notice that the lengths are different. This property says that if you have two irreducible factorizations of the same length, they actually have to be the same. Now, somebody give me an integral domain that has this factorization structure. How would you build such a thing?
Z2 power series x squared x cubed.
That is the most natural thing, I think, to try. Absolutely. Right. Which is basically all power series over Z2 that is missing on your time. Fortunately, it doesn't work. Actually, see if you can figure out, and actually the reason it doesn't work
1 over x.
is because you've got to add stuff and there's other things that creep in. First of all, these aren't your x squared and x cubed. You run into other stuff. And actually the other irreducibles depend on, so you pick Z2, which I would have too, but if you picked a different field, then you would have irreducibles that show up as strange sums. And in fact, here's the following. M0 is multiplicative structure. At least modular units. If you remember, we had that unit problem of many UFDs. In fact, all you have to do is, and we'll talk about all these words later, all you have to do is take any UFD and take any prime in it and localize it that prime, and there you'll have it. Anything works. Even modular units is not the multiplicative structure of in atomics of name. There is no atomic integral domain. I'm gonna get to that word too. What does it mean to be atomic? It means that everything that is not zero and not a unit can actually be factored into irreducibles. This monoid, this one's all over the place. It is impossible to build an atomic integral domain that even has a simple factorization structure as a small multiplicative structure. It's actually more, you can build an integral domain where everything that is atomic factors like this factorization construction, but the construction is necessarily not atomic, which is really weird, and we'll kind of get to that later. So we're going to be talking about factorization in integral domains, factorization in monoids, and this first kind of motivating example, I think, even though I haven't shortened this up in details, but hopefully I will later. This shows you that in a certain sense, it's easier to build things that you want factorization wise in monoids. When you try to do it with domains, sometimes it works and sometimes it doesn't. And even though, well, in fact, because of the fact that rings have this extraneous additive structure that has to be compatible, sometimes there are things that you can't foist on a ring. In particular, you can't build an atomic domain like this. Yes, sir.
You can get kind of close to that if you take a number field with class number greater than 2, right? You just don't, you don't cover you don't cover that particular property there.
If you have a ring or a domain, a ring of algebraic integers, if you will, that has class number bigger than 2, it won't have the half factorial property, which we'll get to later. But it's impossible ever to have this. And actually, there's kind of another problem with this structure. So let me point out, because you bring up a probing question, actually. And we'll get to this when we talk about integrality a little bit. When you have that 2, 3, then you're going to have some element, just for convenience, I'll call it X. This is necessarily a polynomial bigger. You're going to have that in the ring. So in the quotient field, so y'all familiar with the quotient field when they're playing some fraction. One of the things you have in the quotient fields, you have x cubed over x squared, which is x. Right? So notice that x is a root of right. Notice that this polynomial in the variable t squared minus x squared, is actually a polynomial with coefficients in R. Agreed? And notice when you plug in x, this equals 0. Right? And so if you're a ring of integers, it turns out it has to be integral closed. So if it satisfies the root of this polynomial, it'll be this. So when you have this in a ring of algebraic integers, you also have to have the x. So the 2 and 3 give you 1 automatic. But we will dig up that fossil later as well. Okay. Any questions? Let me kind of give you some definitions here. Cherry pick sort of beginning sections, skip over some of the stuff. So I'm following with the notation in my notes right now. Definition. D is a division ring. if so, I've sort of skipped over what a ring is. If there's any questions about that, let me know. Here's some types. We say D is a division ring if every non-zero element of D, if every non-zero element of D is invertible. Yeah, thank you. Thank you. That's what I meant. It's proof under multiplication. A commutative division ring is a field. And definition 1 4. What are the commutative with 1? I don't want to talk about left and right zero divisors, so I'm gonna be lazy. A and R is a zero divisor if there exists R such that AB equals 0. So by this definition, in any ring with identity, 0 is a zero divisor. Right. If 0 is the only zero divisor, and R has 1, then R is an integral element. And as I said earlier, this is where we are going to spend most of our time in integral domains. So let me give you some background on ideals.
Could I ask a quick question?
Sure.
So I think some conventions allow the trivial ring to be an integral domain, so here we're disallowing that.
The trivial ring being the zero ring?
Yeah.
I will never consider that unless I tell you otherwise. I will always assume my ring has 1. Yeah,
Right.
so, I mean, it could be, right, the trivial ring, because you consider 1 to be, or 0 to be the identity in that case, but I'm not gonna get into category theory, so I'm not gonna worry about that. So let me recall for you, R is being ring 1. If you have a non-empty subset, if 1, I is a subgroup of R under addition, and 2, I sucks in the sense that it vacuum cleaners up everything in R. That is to say, for all R in R, Ri is contained in I. So it's a big vacuum cleaner, sucks everything in. This is what we mean to be an ideal. And again, I'm not gonna worry about left ideals, right ideals, etc. Let me give you an example. If R equals Z, what do I know about the ring Z? I know first and foremost it's a group. In fact, it's a cyclic group. And any subgroup of a cyclic group is 0. For 1. NZ, where N is in the natural number Q 0. So if N is 0, then this is just the trivial subgroup. If N is 1, it's the whole thing. And fortunately, any subgroup is cyclic, so we know this. And it's easy to check that these all have the vacuum cleaner property. So in fact, Z is a PID because all the ideals are generated by single element. In fact, you can identify that element as being the smallest positive element with respect to absolute value if the ideal is not 0. So if you have, or generally, if R is medium from 1 and S in R is a subset, this one could even be empty, then the ideal generated by S, so that's the smallest ideal of R that contains S, is the intersection so the ideal generated by whatever the set is just the intersection of all ideals contained. And one can think of this as the smallest ideal of R that contains a set S. And in general, a typical element of this well, in most cases, I'll ask you a question in a minute, is of the form, the sum RISI, where RI is in R and SI is in S. By the way, this is another nice, I'm being very nice to you by assuming the ring is commutative with identity. Look at what the form of ideals look like when you don't have the identity or you're not commutative or both. It is death on a hot plate. Yeah, I don't know why anybody would want to think about that stuff. Let me ask for a special case. What happens if S is the empty set? What's the ideal generated by the empty set? 0. It should be 0 because it's the intersection of all ideals in R that contain the empty set. Well, every subset contains the empty set, and notice that 0 is contained in every one of those. So there you go. Okay. So let me give you a following definition that sort of encompasses several types of ideals. So here's some ideal types, if you will. Let I be an ideal. And let's say that it's generated by some set S. By the way, of course, S is not unique, right? I mean, for example, you could take S to be the entire ideal itself. I mean, there are probably very many generating sets for an ideal. Number one, if A, B, and I implies A is in I or B is in I, we say I is in a more general setting, you see it, if I contains the product of two ideals, it must contain one of the two ideals. But in the community identity case, we can pare it down to this simpler element wise way to think of it. Number two, if I is proper, that is to me, I mean strictly contained in R, and with J ideal implies J equals I, where J equals R, we say I is maximum. Okay, so let me put this like in layperson's terms. Maximal just means you can't put it inside a larger proper ideal. It's as big as possible without blowing up to be the entire ring. 3, if X and R and X to the N and I plus X is in I, we say I is, but no, this one.
Right.
Okay. Or if AB is an I, here again, the elements are all in the ring, maybe an I and A not an I implies B to the N is an I for some N. We say I is primary. And 5, if the size of the generating set can be chosen to be 1, we say I is principal. So let's look at this then. Example. Always good to look at examples. And I'm gonna go easy on this one. Let's go to our old friend Z. Prime numbers. What do they look like? Keep going.
I guess there's one more, right?
Oh, you spoiled my surprise. Yes, yes, he's right. There's another one, right? And 0. That's right. I remember years ago, one of the first times I taught undergraduate abstract algebra, there was somebody doing a continuing education, a high school teacher. And I pointed out that 0 was prime. He was angry. I thought he was like throwing things. It was very upsetting. 2, how about maximums? Right, this time just PZs. How about the radicals?
The NZ.
Yeah, I am radical, that's right. What's that now?
PNZ for E prime.
E
P to the N.
Products of just single run.
Okay, all right. That's kind of weird, right? So basically, it's all the things that form NZ that are square free. There, it's not divisible by any square other than 1. 4. Adam.
P to the N.
There you go. This form, right? Generally speaking, these have nice forms because they're in the integers. Primary, it's kind of a good oh, I don't know, sort of intuitive thing to think of primary ideals as prime powers, but this is not true in general. They're very close to being prime powers. And like a UFD, primary ideals are prime powers, but in general, it can be a little bit more loosey-goosey. And of course, what's the last one? What are the principal ideals? Oh, that's exactly right. So I will. Oh, I am not going to be rude and take your time. Any questions on the stuff?
So, and sometimes my glasses might be playing tricks on me. So in the definition of primary, is that a not an I or implied?
Oh, yes, absolutely. Thank you. Yes, it's a not an I. Yeah. Thank you, thank you. Others, any other notices of my stupidity? All right, well, thank you. I hope you're not too bored so far. Let me know what you think. Going too slow, going too fast. Have some fun, and we will see you all Friday.